What's going on, guys? Justin here, and welcome to our 23rd example video following our course on abstract algebra. Now, today's example video is going to be following the lecture video on polynomial GCDs and PIDs. Now, I do want to apologize for not having a face cam for this video, as I'm having some technical difficulties regarding my face cam, but I decided to go ahead and record this video anyway, so hopefully you don't mind. So looking at this first example, we want to find the GCD of each of the following pairs of polynomials, and then write the GCD as a combination of those polynomials and some functions a of x and b of x. So let's go ahead and get started by looking at number one. So our two polynomials for number one are f of x is equal to x cubed minus 6x squared plus 14x minus 15, and g of x is equal to x cubed minus 8x squared plus 21x minus 18. So we're going to find the GCD and do the extended Euclidean algorithm in order to write the GCD as a combination at the same time. And we're going to do that by dividing g of x out from f of x using polynomial long division, as you saw in the lecture video. So let's go ahead and set up our long division here. So we have x cubed minus 8x squared plus 21x minus 18. And we're going to divide f of x, which is x cubed minus 6x squared plus 14x minus 15. Now, Michael did a lot of examples of this in the lecture video, so I'm sure you know how this works, but basically we want to multiply our leading coefficient of our term that we're dividing by so that it is exactly the same as the leading term of, in this case, our f of x, and then we will group and subtract. So in this case, all we need to do is multiply by 1. So basically, we're just going to be subtracting our g of x from f of x. So let's go ahead and write that out. So we have x cubed minus 8x plus 21x minus 18. And then we're going to group and subtract. So when we subtract, we will get rid of our x cubes. Our minus 8x will become a plus 8x. Sorry, that should be an 8x squared. So we'll have plus 8x, and so we'll have 8x squared minus 6x squared. So that'll just give us a 2x squared here. We have minus 21x plus 14x, and that's just going to be minus 7x. And then lastly, we have 18 minus 15, which is just plus 3. Great. And so we can see now the degree of this remainder here is less than the degree of our polynomial that we are dividing by, so we will go ahead and start over to continue the extended Euclidean algorithm. So now we're going to divide our g of x, which is x cubed minus 8x squared, plus 21x minus 18 by our remainder, which we just calculated as 2x squared minus 7x plus 3. And we're going to continue doing this kind of nested division until we can't divide anymore, and that will be our GCD, and then we can use back substitution in order to write it as a combination. So let's go ahead and divide this now. So we have 2x squared out front like that, so we need to multiply by 1/2 x in order to get an x cubed. So when we multiply by 1/2 x, we'll get an x cubed here as we want. And then we'll have minus 7/2 x squared. And then lastly, plus 3/2 x. Great. So then we are going to group and subtract. Well, let's see what we get. Well, our x cubes are going to cancel out. Then we'll have a plus 7/2 x squared. So what happens when we add 7/2 to negative 8? Well, let's see, negative 8 is negative 16/2, so that's going to give us negative 9/2 x squared. And then we have 21x minus 3/2 x. Well, 21x is 42/2, and since we're subtracting 3 from 42, that will give us 39/2, so we'll have plus 39/2 x, and then we can just drop that negative 18 down here. Great. So now we want to see what we need to multiply our 2x squared over here by in order to get negative 9/2, but that's going to be, well, let's see, 9 over 4, because the 4 will cancel the 2 out, and then we will have a 9 over 2, so it's going to be negative 9 over 4, and we don't need to multiply by an x there because it's already the same degree as what we want. So that'll give us 9/2 x squared. And then let's see, when we multiply negative 9 over 4 into our 7 there, we will get, well, what's 9 times 7? That's going to be 63. So we will have a positive in this case because our negatives will cancel out, 63 over 4x. And then lastly, we have negative 9 over 4 times positive 3. Well, we will have a negative 3 times 9, which is 27 over 4. So that'll be negative 27 over 4 there. Great, so now we will group and subtract. And so once we subtract, we will cancel out our x squared terms. And then let's see what we get when we subtract 63/4 from 39 halves. Well, we will get a 15x over 4 for that, and then we will have minus 45 over 4 over here, as we are adding 27/4 to negative 18. Great. And so we can see now that our remainder is a lesser degree than what we divided by, we can then go ahead and redo our division here. So we're going to be dividing our 2x squared minus 7x plus 3 by our remainder over here. So let's go ahead and write that out. So we have 15x, I'll just go ahead and write this as one fraction, minus 45 all over 4. We are dividing our previous remainder, which was 2x squared minus 7x plus 3. Great. And so keeping in mind that our leading coefficient in this case is 15x over 4, we want to see what we would need to multiply in order to get 2x squared. Well, let's see, we want a 2 in our numerator and nothing in our denominator. So to accomplish that, let's multiply by 8x over 15. As the 15 will clear the numerator and the 8 will cancel the denominator and leave us with a 2 in the numerator there. Great. And we want to keep it positive because our term here is also positive. So let's go ahead and see what we get when we multiply by that. Well, that's just going to give us, like I said, 2x squared. And then let's see what happens when we multiply by 8x over 15 into 45 over 4. Well, something similar will happen. We will just be left with negative 6x, as our 15 will cancel the 45 down to a negative 3, and the 8 will clear our denominator nicely and leave us with a 2 in the numerator. So we'll have negative 3 times 2, which is negative 6. Great. So now we will group and subtract. That'll cancel out our 2x squareds, and then we will have plus 6x into a negative 7x, which will just leave us with minus x plus 3. And now we need one more multiple to finish this division off and finish our series of divisions off. So we can see that if we multiply by negative 4 over 15, we will get our negative x in front as desired. So that will give us a negative x. And then if we multiply by negative 4 over 15 into the other term, we will have plus 3. And so we can see if we subtract here, we will simply be left with 0, which means that our GCD here is negative x plus 3. So at this point, you could use back substitution, writing these division problems as equations and plugging them back in all the way back into our original equation here. But I'll just go ahead and write out for you the combination of f of x and g of x, which gives us our GCD. And that's given by the following here, where we have x cubed minus 6x squared plus 14x minus 15 times 2x minus 9 over 15 minus x cubed minus x squared plus 21x minus 18 times 2x minus 5 over 15 is equal to our desired GCD, negative x plus 3. And so we can see in this case, this would be our a of x here, and this would be our b of x, as desired from the problem statement. Great. So that finishes off part 1 for this problem here. So let's go ahead and get into part 2, where we are going to do a division like this, both in Z5 and in Z3. So for part 2 of this problem, we have two new functions given by x cubed plus x squared minus 4x plus 4, and g of x given by x cubed plus 3x minus 2. And we want to do what we just did, but both in Z5 and in Z3. So let's start by doing it in Z5. Or Z5 adjoined x, I should say. So in Z5 adjoined x, let's see if we can simplify these polynomials any. Well, we can write f of x in the following way. We'll have f of x is equal to x cubed plus x squared. And then let's go ahead and turn that minus 4x into just a plus x, because negative 4 is simply equal to 1 in Z5. That should simplify things. And then we can leave this plus 4 as it is, just so that we have a positive number there. And then let's see if we can rewrite g of x in any way. Well, we'll have g of x is equal to x cubed, and then we'll keep our plus 3x there, but let's change our minus 2 into a plus 3. Great. So now let's go ahead and divide f of x by g of x to get our GCD. So we're going to be dividing x cubed plus x squared plus x plus 4 by our g of x, which is given by x cubed plus 3x plus 3, Well, just like before, we only need to multiply by 1 for this first one, and that will give us x cubed plus 3x. Well, we write the 3x over here, so our terms are lined up nicely, and then we'll have a plus 3, and then we will group and subtract. So once we subtract, we can bring our x squared down, and our x cubes will cancel, and then we'll have x minus 3x, which is negative 2x. By keeping in mind that we are in Z5, negative 2x is simply equal to 3x, so this will give us a plus 3x here. And then we'll have 4 minus 3, but that's just plus 1. So that's what we'll get for our remainder here, and because the degree of our remainder is less than our divisor, we can go ahead and start our division again. So now we're going to divide our g of x, x cubed plus 3x plus 3, by what we just got for our remainder there. That'll be x squared plus 3x plus 1. So let's go ahead and do that. So we need to multiply by just x in order to match up our leading coefficients. And when we do that, we will get x cubed plus 3x squared plus x. So we will then group and subtract. So we can see we will get our x cubes will cancel out, and we will get a negative 3x squared, but negative 3 is just 2, so we'll have 2x squared. And then we have 3x minus x, but that's just plus 2x. And then we can bring our 3 down, and we will have a plus 3 here. Great. So now in order to match up our leading coefficients, we need to multiply by a 2. So we have a 2 there. So we'll have 2x squared plus 6x plus 2. And then we will group and subtract. Once we do that, our x squared terms will cancel out. And we have 2x minus 6x. Well, that's going to be negative 4x, or just 1x. Then we have 3 minus 2, so we are left with an x plus 1. Great. Well, since our remainder is of lesser degree than our divisor, we can go ahead and start our division again. So let's go ahead and divide our x squared plus 3x plus 1 by x plus 1 here. And all we need to do is multiply by x for this to work out. So we get x squared plus x, and then we will group and subtract. And we'll get 3x minus x, which is just 2x. And then we can bring our plus 1 down. And then all we have to do is multiply by 2 here in order to match up our leading coefficients. So once we multiply by 2, we will have 2x plus 2. And we will group and subtract. Our 2x's will cancel out, and we'll have 1 minus 2, which is negative 1, or just 4 as our remainder here. Great. So I'll leave it to you to take this division and go ahead and back substitute to find out the linear combination for f of x and g of x. I'm just going to omit it for the sake of brevity like I did for the first one, but I will go ahead and do the polynomial long division for z3 as well. So let's go ahead and get into that. So we're going to be doing the exact same division as we just did, but we're going to be doing it in z3 this time, or z3 adjoin x. So in z3 adjoin x, let's see how we can possibly simplify our two functions. So f of x will still be equal to, we'll have x cubed plus x squared, but then we can reduce that negative 4x to be just a negative 1x, and negative 1 is equal to 2, so we'll have a plus 2x in this case, and then we can have a plus 1 here, as 4 is just 1 mod 3. And then we will have g of x, and g of x is x cubed. Then we have plus 3x, but that's just 0 in z3, so we'll have x cubed minus 2, but let's go ahead and rewrite that minus 2 as just a 1, so we have x cubed plus 1. So our g of x actually got simplified quite a bit from us taking it in z3. So let's go ahead and divide our f of x by our g of x now. So we have x cubed plus x squared plus 2x plus 1. We are dividing by our g of x, which is given by x cubed plus 1. Now all we need to do is multiply by 1 to match up those leading coefficients, and we'll have x cubed and then a plus 1 over here. We will then group and subtract, and once we do that, we'll be left with x squared plus 2x, and our 1's will cancel out. So now we want to divide our g of x by this new remainder. So we'll have x cubed plus 1, and we are dividing by x squared plus 2x. Well, all we need to do is multiply by x to match up those leading coefficients, and then we'll have x cubed plus 2x squared. So then we will group and subtract, and once we do that, our x cubes will cancel out. We'll get negative 2x squared, but negative 2 is just 1 in z3, so we'll have x squared plus 1 left here. And all we need to do is multiply by 1 in order to match up our leading coefficients there. So we'll have x squared plus 2x, and then we will group and subtract once again. So our x squareds will cancel out, and we'll be left with a negative 2x, which is, of course, just x, and then we can bring down our 1 again, and we will be left with an x plus 1. So now we can go ahead and do our next division. So we'll have x squared plus 2x, and we will be dividing by x plus 1, and all we need to do is multiply by x to match up those coefficients. So we'll have x squared plus x, then we group and subtract, and what we're left with is 2x minus x, which is just x. And all we need to do is multiply by 1 there, and once we multiply by 1, we'll have x and x plus 1, and then we will group and subtract, and we'll be left with negative 1 or 2 as our remainder. So that finishes off the polynomial long division for this one. And like I said, I will leave off the back substitution just for the sake of brevity, as it is rather tedious to work out on paper like this. But feel free to work that out on your own and post what you got in the comments. So let's go ahead and get into our next example. So for our next example, we want to find all the zeros of the polynomial 5x cubed plus 4x squared minus x plus 9 in z12, z2, z3, and z7. Great. So let's start by finding these zeros in Z2. So let's go ahead and write that we are working in Z2. So in Z2, we can rewrite our polynomial in the following way. We'll have 5x cubed, we can write as just x cubed. Then we'll have 4x squared, but 4 goes to 0 in Z2, so that term will completely disappear. And then we have a negative x here, but in Z2, negative 1 and 1 are the same. So let's just go ahead and write that as a plus x. And then we'll be left with plus 9, but that is also 1. So in Z2, we can rewrite our polynomial as x cubed plus x plus 1. Now, in order to find the zeros, what we want to do is plug in all the values in Z2 and see which ones will give us 0. So fortunately for us, there's only 2 values to plug in for Z2. And let me just go ahead and write this function as f of x so that I can use this notation when we're plugging in different values. So f of 0 is going to be obviously equal to 1 in this case. So 0 does not work as a 0 for this polynomial in Z2. And then f of 1, well, for f of 1, we're going to get a 1 plus 1 plus 1. But 1 plus 1 is 0, and that will also just be leaving us with a 1. So there are no zeros in Z2 in this case. So next, let's go ahead and move on to Z3. So in Z3, let's go ahead and first start out by rewriting our polynomial. Well, we can reduce 5x cubed to just be 2x cubed. Then our 4x squared will simply be plus x squared. And then our minus x will be a plus 2x. And then we can write our 9 as 0, so we'll just omit that there. So just like we did before, we're going to plug in all values of Z3 into the coefficients and see if we get 0. And right off the bat, we can see that if we plug 0 into this polynomial here, we will get 0 as we intended. So f of 0 is going to be equal to 0 and then be a 0 for this polynomial. Next, let's go ahead and plug in 1. So we'll do f of 1 here. Well, f of 1 is simply going to be equal to, well, we'll have 2 times 1 cubed, which is just 2. So that'll give us a 2. Then we'll have plus 1 from our x squared, and then plus another 2 there. Well, this 2 plus 1 is going to go to 0, and we'll just be left with 2, which means that 1 is not a 0 either. So lastly, in Z3, we have f of 2, but we can also write that as f of negative 1 just to simplify our calculation a little bit. And so when we plug in negative 1, we'll get a negative 2 for this first entry here. Then we'll have plus 1, and then we will have another negative 2 here. But negative 2 is just the same as 1, so we'll have this is equal to 1 plus 1 plus 1. But 1 plus 1 plus 1 is equal to 3, so this is equal to 0 in Z3, which means this is also a 0. So for Z3, our zeros are 0 and 2. Great. So let's go ahead and move on to Z7. So in Z7, we can write our polynomial in the following way. Well, all the coefficients we can keep the same, except for our plus 9 there. So let's write this as 5x cubed plus 4x squared minus x plus 2. And then just the same we have been doing, we're going to be plugging in all values for Z7. So starting off with the easiest, let's start off with f of 0. Well, f of 0 is going to be equal to all of our x terms zeroed out, and we'll just be left with our 2. So that does not work. Next, let's look at f of 1. Well, f of 1 is going to give us a 5 for our first term, a 4 for our second term, a -1 for our third term, and then we will have that plus 2 there at the end. Well, we can see we can combine this 5 and this 2 to make a 7, which will be 0. And then we have 4 minus 1, which is equal to 3. So this does not work as well. Next, let's go ahead and check f of 2. Well, let's see, we'll have 5 times 2 cubed. 2 cubed is 8, and we'll have 5 times 8, which is 40. And 40 is equal to 5 in Z7 because it's 5 more than 35. So that will be equal to 5 here. Next, we have 4x squared. Well, 2 squared is 4. We'll have 4 times 4, which is 16, which is equal to 2 in Z7. Then we'll have a minus 2 here, and then lastly a plus 2 there. And so we can see 2 will work because this 5 plus 2 will be a 7, and this -2 and 2 will cancel out. And so f of 2 will simply be equal to 0, which gives us our first 0 in Z7, which is 2. So next, let's look at f of 3. So f of 3 is going to be 5 times 27. And let's see, that's going to be 5 times 20 plus 5 times 7, so that will give us 135. And 49 plus 49 is 98. And 7 times 5 is 35, so this will be 2. So that's what we'll get for our first term. For our second term, we'll have 4 times 7 squared, which is 49, which is the same as 98 times 2, which is the same as 196. And for our second term, we will have 4 times 3 squared. 3 squared is 9, so we'll have 4 times 9, which is 36, so we'll have a plus 1 here. Then we'll have minus 3, but minus 3 is just equal to 4. And so these first three terms will cancel out. Then we'll be left with our plus 2 here at the end. So this whole thing will be equal to 2. So this is not a 0. And so next, instead of continuing to complicate the math, we're going to look at f of -3 and -2 and -1 to finish this off. So let's look at f of -3, noting that -3 is equal to 4 in Z7. So 5 times -3 cubed is just going to be -2, as we already know that 5 times 3 cubed is 2, and so -2 is 5, so that will give us a 5 for our first term. For our second term, we will have just 9 times 4 once again, so that'll give us a plus 1 here. Then we'll have a -3, which is just a regular 3, so we'll have plus 3, and then plus 2 here. So this 5 and 2 will be 0, and then we'll be left with a 4 here, which is of course not a 0. And so now we have -2. So f of -2 is going to be equal to 5 times -2 cubed, but -2 cubed is -8. Then we'll have 5 times -8, which is -40. And since we already know that 40 is 5, it'll just be -5, and -5 is simply equal to 2. So we'll get a 2 from that first term. For our second term, we'll have 4 times x squared, but -2 squared is just 4. So we'll be left with 4 times 4, which is 16, which is also 2. And then we'll have minus x, but minus -2 is just 2, so we'll have one more 2 there. And look at that, what we're left with is just another 2, so we have 4 2's here, and that's going to be equal to 8, which is just 1. So -2 is also not a 0. And then what we have last is f of -1, which is of course equal to 6 in Z7. So f of -1 is going to be equal to -5, which is 2, plus 4 times -1 squared, which is just 1, so that'll be plus 4 here. And we'll have -1, which is 1, so we'll have a 1 there, and all of these terms will go to 0, and then we will have our plus 2 at the end like always. So this is equal to 2 and also not a 0. So that means our only 0 in Z7 is 2. And lastly, we would want to check all of the zeros in Z12, but I'll just go ahead and verbally say that there are no zeros in Z12, but feel free to check that out on your own in your free time. But if you want to go through all of Z12 by exhaustion, feel free to do that. You just use the same method, which I've already demonstrated here for the other 3. So let's go ahead and get into our next example. So for this one, we want to find all irreducible polynomials of degree 2 and 3 in Z2. Now I want to note that any polynomial which is irreducible in Z2 by the method we've already been using will need to be equal to 0 for some value in Z2. But fortunately for us, there are only two choices in Z2, 0 and 1. And if neither of those can be 0, that means that we must have that for some function f of x, f of 1 is equal to f of 0, which is equal to 1. Great. So now all we need to do is come up with polynomials that are of degree 2 and 3, where f of 1 and f of 0 are both equal to 1. So it's pretty easy to see that if we're dealing with a second degree polynomial, we don't have many choices here. In fact, the only choice that we can pick is x squared plus x plus 1. And so you can very easily verify that you're going to get 1 if you plug in a 1 or a 0 into our x there, as we'll have 1 plus 1 plus 1, which is just 1 in Z2, or just the plus 1, which is of course just 1. And so in the same vein as that, we can look at our third degree polynomials here, and we will actually have two choices for our possible third degree polynomials that satisfy this condition right here. We'll have x cubed plus x plus 1, and we will also have x cubed plus x squared plus 1. And those will be the only choices for third degree polynomials, just due to how restrictive Z2 is. So those are all of our irreducible polynomials of degree 2. It's pretty straightforward once you realize this condition that I wrote at the top here. I found this to be one of the problems that you would not want to overcomplicate. So let's go ahead and get to the next example. So for this one, this is actually very straightforward. We just want to find two different factorizations of x cubed plus 11x squared plus 10x in Z12. Well, let's go ahead and note that we can factor out an x from this polynomial to start with, and that will give us a quadratic, which we will like to see. So once we factor out an x, we will have x times x squared plus 11x, and then plus 10. And it's very easy to see that that will factor as x times x minus 10 and x minus 1, which is our first factorization of our polynomial. But of course, using the rules of Z12, we can rewrite this as x times, well, negative 10 is equal to 2 in Z12, so x plus 2, and negative 1 is equal to 11 in Z12, so that'll be x plus 11, and that will give us our second factorization of this polynomial in Z12. So that was pretty straightforward. Let's go ahead and get into our next one. So for this next result, we want to show that if f is a field, that f adjoin x1 through xn is an integral domain. And so this is actually kind of a corollary to a result that Michael proved in one of the lecture videos before this example video. And so what he proved is that if f is a field, that implies that f adjoin x is an integral domain. And so one of the things to note about this proof is that f being a field means that it is also an integral domain. So that's kind of in the background there. But like I said, given that this was proven in the lecture video, we can use that fact, and we can use this as our base case for a proof by induction. So for this base case would be proven in the lecture video, and now all we need to do is demonstrate the induction step. So let's go ahead and do that now. So let's suppose that we have a field f. So suppose f is a field, and I'll go ahead and put in quotes, and thus an integral domain. And we have, for some k, which is between 1 and n, f adjoin x1 through xn is an integral domain, or I should say x sub k here. Then f adjoin x sub 1 all the way up to x sub k and x sub k plus 1 can be written in the following way as the product of f adjoin x1 all the way up to x sub k and f adjoin x sub k plus 1, which finishes this off. So that is an integral domain, and that is because what I've underlined in blue, or I'll go ahead and refer to that as just blue box, is an integral domain. Great. So we can see this result's kind of trivial once you prove the base case, but it is an important thing to keep in mind. I think Michael may have even outlined some of the logic for this result when he went over the base case. But anyway, let's go ahead and get into our last example. So for our last example, we're going to let p of x be an irreducible polynomial in f adjoint x, where f is a field. We want to suppose that p of x divides the product of f of x and g of x, and show that p of x either divides f of x or p of x divides g of x. So we're going to do this proof by way of contradiction, and we're going to break it into some cases. So let's start with case 1. And case 1 is going to be that both f of x and g of x are irreducible. But we can see that this case automatically is impossible, as that would mean that the only divisors of the product of f of x and g of x are f of x and g of x. And that goes against our supposition that p of x divides f of x times g of x. So then for case 2, let's suppose that either f of x or g of x is irreducible, so that only one of them is irreducible. And without loss of generality, let's go ahead and suppose that f of x is the irreducible one. Well, if f of x is irreducible and p of x divides the product of f of x and g of x, that immediately implies that g of x must divide p of x. And without loss of generality, that would also mean, if we suppose that g of x was the irreducible one, that f of x would divide p of x. Oh, and this is case 2. And so let's go ahead and lastly look at case 3. And case 3 is f of x and g of x are both reducible. So if f of x and g of x are both reducible, then we can write them in the following way: as a product of their factors. We can write it as the product from 1 to m. And let's express those factors as h sub I to the k sub I of x. And similarly for g of x, we can write it as a product as well. And we'll take that as the product from 1 to n of, let's just call them q sub I to the l sub I of x. But we know that p of x divides f of x and g of x. So what does that mean? That means that p of x must be expressible as a product of our h sub I of x and our q sub I of x. But that is a contradiction, as if you recall, we have supposed at the start that p of x is an irreducible polynomial, which means that this case must also be impossible. So the only case that is possible is that p of x divides f of x or p of x divides g of x. And just saying that, I realized I wrote this division backwards. This implies in this case that p of x divides g of x. That's of course obvious from the fact that we are using the fact that f of x is irreducible in order to show this divisibility. Okay, great. So that finishes this last problem off, and that's a good place to stop.